Now in this lecture we'll answer on two questions. In the first question we find out the area of this circle that is inside square ABCD, and in the second question we find out the area of the green shape that is inside a quarter circle. We start with the first question. In the drawing we have square ABCD. Inside square ABCD we have a circle. We know that angle CBT equals to 30 degrees, line segment PD equals to 5 units, and our mission is to find out the area of this circle. So first of all we define the center of this circle as O. We will join points O and Q together by a straight line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of the circle, that is equal to, we define the radius of the circle as R, so OQ equals to R. We have the radius OQ that is drawn to the point of tendency, therefore according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. This angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we'll join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle that is equal to R. We have the radius OP that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. We also know that all the angles inside square ABCD are equal to 90 degrees, so this angle equals to 90 degrees in square ABCD. This angle, it is also equals to 90 degrees. This angle equals to 90 degrees, and finally this angle equals to 90 degrees. So actually inside quadrilateral AQPO, inside this quadrilateral we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total they must be equal to 360 degrees. Therefore this angle must be equal to 90 degrees. In order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So we found out inside quadrilateral AQPO we have 4 right angles. Therefore, this quadrilateral AQPO is a rectangle. So I write it down. Quadrilateral AQPO is a rectangle. Why? Because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle AQPO, PO must be equal to AQ. PO equals to AQ. But we have already found out that PO equals to R. Is the radius of the circle. And from this equation, R equals to PO equals to AQ, we will derive that AQ is also equals to R. AQ equals to R. So you can write here in the drawing that AQ equals to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that AP equals to QO. AP equals to QO. But we have already found out that QO equals to R. It is the radius of the circle. And from this equation, AP equals to QO equals to R, we will derive that AP is also equals to R. Here AP equals to R. So we actually found out that quadrilateral AQPO is a square and not a rectangle because of the fact that all of its sides are equal to each other, they are equal to R. So you can write down that quadrilateral AQPO is a square. We also know that all the sides of square ABCD are equal to each other. That is to say, side AD equals to side AB. AB equals to AD. AB equals to AD in square ABCD. AB equals to AD in square ABCD. What is the value of AB? AB equals to R plus QB. AB equals to R plus QB. What is the value of side AD of square ABCD? It is equal to R plus 5. R plus 5. So in conclusion, we found out that R plus QB equals to R plus 5. Here we subtract R from this equation. So R will get cancelled and we left only with QB that is equal to 5. So we found out that 9 segment QB equals to 5 units. You write down in the drawing that QB equals to 5 units. In the next step, I present to you rule number 2 and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From the common external point P, we have tangent PA and also tangent PB. And according to this rule number 2, PA equals to PB. We can implement rule number 2 in our drawing. Why? Because in our drawing, if we focus on the common external point B, from this common external point B, we have tangent BQ and also tangent BS. And according to rule number 2, they are equal to each other. That is to say, BQ equals to BS. But we have already found out that BQ equals to 5 units. So here, and from this equation 5 equals to BQ equals to BS, we derive that BS is also equals to 5 units. BS equals to 5 units. Here we can write down that BS equals to 5 units. In the next step, we'll join points Q and S together by a straight line. By joining points Q and S by a straight line, we created here triangle QBS. What is the size of angle QBS? What is the size of this angle? This angle, it is very easy to see from the drawing. the size of this angle equals to angle ABC. Angle ABC that is equal to 90 degrees minus angle TBC that is equal to 30 degrees. That is to say 90 degrees minus 30 degrees is the size of this angle. 90 degrees minus 30 degrees, it is 60 degrees. We'll continue to focus on triangle QBS. In this triangle QBS, side QB equals to side BS. They are both equal to 5 units, therefore they are equal to each other. So QB equals to BS. And we have the rule that in front of equal sides in the triangle, there are equal angles. So in front of those two sides, we have those two angles. Therefore, those two angles must be also equal to each other because of the fact that they are located in front of equal sides. Okay? So if this angle is equal to alpha, then this angle must be also equal to alpha because of the fact that those two angles that are located in front of equal sides must be also equal to each other. So those two angles, they are both equal to alpha in triangle QBS. But we have already found out that this angle equals to 60 degrees. Okay? So 180 degrees minus 60 degrees, it will be the sum of those two angles. Okay? According to the rule that the sum of the angles in any triangle, the sum of those two angles must be equal to 180 degrees minus 60 degrees. 180 degrees minus 60 degrees is 120 degrees. So we found out that 120 degrees equals to alpha plus alpha. So in triangle QBS, in triangle QBS, we found out that alpha plus alpha equals to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. We divide this equation by 2 and we get that alpha equals to 60 degrees. Here alpha equals to 60 degrees. So those two angles are equal to 60 degrees. So we actually found out that inside triangle QBS, we have all angles are equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle. Triangle QBS is an equilateral triangle. And we know that all the angles of an equilateral, all the sides of an equilateral triangle are equal to each other. Side QB equals to side PS. They are both equal to 5 units. And side QS, therefore, must be also equal to 5 units. So here you can write down that QS must be also equal to 5 units. QS equals to 5 units in the equilateral triangle, triangle QBS. In the next step, we will join points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of this circle that is equal to r. We have the radius OS that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. In the next step, I will copy quadrilateral SOQB in a new page and we will analyze quadrilateral SOQB. Angle OSB equals to 90 degrees according to rule number 1. So this is quadrilateral QBOS that I copied from the original drawing. In quadrilateral QBS, this angle is the missing angle. So what is the size of the missing angle? Angle QOS. Angle QOS, the missing angle, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, the size of the missing angle, angle QOS, will be equal to 360 degrees minus the sum of three other angles, minus 90 degrees plus 90 degrees plus 60 degrees. Okay? So the size of the missing angle, angle QOS, will be equal to 360 degrees minus 90 degrees plus 90 degrees is 180 degrees, and 180 degrees plus 60 degrees is 240 degrees. So we found out that the size of the missing angle equals to 360 degrees minus 240 degrees, it is 120 degrees. So the missing angle equals to 120 degrees. Angle QOS equals to 120 degrees. We can write down in the drawing that the missing angle, angle QOS, equals to 120 degrees. So, in the next step, I will present to you the law of cosines, and we will implement the law of cosines in this green triangle, triangle QOS. So, what is the law of cosines? The law of cosines is true in any triangle. So here we have this is the law of cosines. So if we have triangle ABC that could be any triangle, this is triangle ABC. And we know that the length of side AB is A units, the length of side AC is B units, and the length of side BC is C units, and the angle between side AB and side AC is theta. Then according to the law of cosines, this triangle ABC, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I'll repeat again, in this triangle ABC, that could be any triangle, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. In the next step, we will implement the law of cosines in the green triangle QOS. So I copy triangle QOS in this new page, and we will implement the law of cosines in this triangle. So this is my triangle QOS, the copied from the original drawing. QS equals to 5 units, QO equals to R, OS also equals to R. Okay, so according to the law of cosines, we get that in this right triangle QOS, 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. Okay, so 5 squared is 25. Again, 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. 5 squared is 25, R squared plus R squared is 2R squared, minus 2R times R is minus 2R squared, cosine 120 degrees equals to minus 1/2. So we substitute cosine 120 degrees by minus 1/2. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus, so this expression in total will be equal to plus R squared. So 25 equals to 2R squared plus R squared is 3R squared. We divide this equation by 3 and we get that R squared equals to 25 over 3. We know that the area of any circle is equal to pi R squared. But we have already found out that R squared equals to 25 over 3, therefore we can substitute R squared in this equation by 25 over 3, so we'll do it now. We get that the area of our specific circle equals to pi times R squared, and R squared is 25 over 3. So in conclusion, we found out that the area of our circle equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. So we finished with the first question. In the next step, I'll present to you the second question, and we will answer the second question in 3 different methods. In the drawing, we have a quarter circle. Inside this quarter circle, we have small circle. We know that here it is actually line segment CD. Here, line segment CD equals to 8 units. Angle ACD equals to 90 degrees, and our mission is to find out the area of the green shape. We'll start with the first method, and we will define the center of the small circle as J. We'll define the point of tendency of tangent CD if the small circle is E. We will define the point of tendency of tangent OB with the small circle as F. We will join points J and D together by a straight line. Point J is the center of the small circle, point E is the point of the small circle itself, therefore JE is the radius of the small circle that we will define as R. We have the radius JE that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we join points J and F together by a straight line. Point J is the center of the circle, point F is the point of the circle itself, therefore JF, it is the radius of the circle that is equal to R, and we have the radius JF that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, because of the fact that AOB is a quarter circle, point O must be the center of the quarter circle, angle AOB, this angle must be equal to 90 degrees, and in addition, AO must be the radius of the quarter circle that we define as capital R. The radius of the quarter circle equals to capital R according to our definition. Okay. So here, AO is the radius of the quarter circle. So AO as a radius, it is absolutely a straight line. Okay, AO is a radius, it is absolutely a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have at this side of AO at point C? We have this angle that is equal to 90 degrees plus this angle. In total, the sum of those two angles must be equal to 180 degrees according to rule number 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So therefore the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees. This angle must be equal to 90 degrees. In the next step, from the center of the small circle, that is to say from point J, we will go perpendicular on CO. So here, this angle equals to 90 degrees, and this angle it is also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point J and CO as T. So inside the small quadrilateral CETJ, the upper quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Likewise, we focus on the small lower quadrilateral TJOF. Inside quadrilateral TJOF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So we actually found out that this angle EJF, this angle equals to 90 degrees plus 90 degrees, that is 180 degrees. And angle EJF equals to 180 degrees. Therefore, angle EJF is a straight line. Any angle that is equal to 180 degrees, it is a straight line. If angle EJF is a straight line, it means that EJF is also a straight line, and if EJF is a straight line, then EF is also a straight line. EF is also a straight line. So we can write down that EF is a straight line. And if EF is a straight line, it means that quadrilateral CEFO is a rectangle. I'll write it down. Quadrilateral CEFO is a rectangle. Why? Because quadrilateral CEFO has 4 right angles. That is the reason that is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to EF. CO equals to EF, according to the rule that the opposite sides of a rectangle are equal to each other. But we have already found out that EF equals to R plus R, that is 2R. And from this equation, CO equals to EF equals to 2R, we will derive that CO is also equals to 2R. CO equals to 2R. Okay, so in the next step, we will join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself. Therefore, OD is the radius of the quarter circle that is equal to capital R according to our definition. In the next step, we will implement the Pythagoras theorem on the right green triangle, triangle OCD. So, here, in the right green triangle, triangle OCD, here by PT is evaluation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle OCD is OD. Therefore, the square of the hypotenuse is OD squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to CO squared plus CD squared. I'll repeat again, in the right triangle, triangle OCD, according to the Pythagoras theorem, OD squared equals to CO squared plus CD squared. OD equals to capital R, therefore OD squared is capital R squared. That is equal to CO squared. CO equals to 2R, therefore CO squared equals to 2R squared, that is 4R squared. Plus CD squared. CD equals to 8 units according to what is given as the question, therefore CD squared is 8 squared, that is 64. So in conclusion, found out that according to equation number 1, capital R squared equals to 4R squared plus 64. Here we subtract 4R squared from this equation, equation number 1, and we get that according to equation number 1, capital R squared minus 4R squared equals to 64. Okay? But what is actually the area of the green shape? The area of the green shape, it is very easy to see from the drawing that the area of the green shape is equal to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. So here, what is the area of the quarter circle? The area of the quarter circle is equal to the area of the circle over 4. The area of the circle is pi times capital R squared, And if we divide it by 4, we get that the area of the quarter circle equals to pi times capital R square over 4. Minus the area of the circle equals to pi R square, of course. Here we take pi over 4 as a common factor out of those two expressions. So what is left from pi times capital R square over 4, we took from it pi over 4 as a common factor. What is left is actually capital R square. What is left from minus times pi capital, what is left from minus pi R square after we took from it pi over 4 as a common factor? What is left? It is actually minus 4R square. Why? Because minus 4R square times pi over 4 equals exactly to minus pi R square. So here we have the expression capital R square minus 4R square, but we have already found out that capital R square minus 4R square equals to 64. Therefore, we can substitute capital R square minus 4R square in this equation by 64. We do it now, we get that this expression will be equal to pi over 4 times 64. 64 over 4 is 16, so this expression in total equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. We finished with the first method. In the next step I present to you the second method to find out the area of this green shape. In the second method, we use all the things that we have already found out in the first method. We have already found out that CO equals to 2R. AO is the radius of the quarter circle that is equal to capital R. This angle equals to 90 degrees. So according to number 3. And this angle, it is also equal to 90 degrees. What is the value of AC? AC equals to AO minus CO. Again, AC equals to AO minus CO. Is equal to AO minus CO. So AC equals to AO, that is equal to capital R, it is the radius of the quarter circle, minus CO. CO equals to 2R. So in conclusion, we found out that AC equals to capital R minus 2R. So in the next step, we complete the quarter circle to a circle. Here it is R. So we complete the quarter circle to a circle. So we completed the quarter circle to a circle. We'll extend the radius AO by straight line until it touches the circle. we define the touching point of the extended radius AO and the circle as point T. In the next step, we will extend the straight line DC by straight line until it touches the circle, and we'll define the touching point of the extended straight line DC and the circle as point M. In the next step, we'll join points O and M together by straight line. Point O is the center of the big circle, point M is the point on the big circle itself, therefore OM is the radius of the big circle that is equal to capital R. Likewise, we join points O and D together by straight line. Point O is the center of the circle, point D is the point on the circle, on the big circle itself, therefore OD is the radius of the big circle that is equal to capital R. Here we extended the straight line DC by straight line. When you extend the straight line by straight line, the result must be a straight line. Therefore DM must be a straight line. So if we focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees according to rule number 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the lower side of DM at point C? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 90 degrees. In order to complete the sum of the angles on the lower side of the straight line DM to 180 degrees, at point C to 180 degrees, this angle must be equal to 90 degrees. So we have here two right triangles, right triangle CDO and the right triangle OCM. We will prove that those two right triangles can go into each other. Why those two right triangles can go into each other? So here we have triangle COD, the right green triangle, triangle COD. We prove that it converges to the right triangle, triangle OCM. So why those two right triangles can go into each other? First of all, side CO is a common side that belongs to both triangles, so CO equals to itself. It's a common side that belongs to both triangles. In addition, side MO equals to side OD. They are both the radii of the circle, of the big circle, therefore they are equal to each other. So MO equals to OD. They are both equal to the radius of the big circle that is equal to capital R. So actually prove CO equals to itself is a common side that belongs to both triangles, and MO, the hypotenuse MO equals to the hypotenuse OD. They are both equal to the radius of the big circle that is equals to capital R. By proving that the hypotenuse and one perpendicular can go into those two right triangles, we actually proved that those two right triangles can go into each other, and I will explain you why. Because if, for example, we have two right triangles, we have the right triangle, triangle ABC. This is the right triangle, triangle ABC. It has the hypotenuse AC equals to 5 units and the perpendicular AB equals to 4 units. And you have second right triangle, triangle DEF. We have the right triangle DEF, in this right triangle, triangle DEF. The hypotenuse DF, it is also equals to 5 units, and the perpendicular DO, it is also equals to 4 units. So those two right triangles can go into each other in their perpendiculars, and one in one perpendicular, and in their hypotenuses. Okay, AC equals to DE, and AB equals to DE, and AC equals to DF. So here the third side, BC, must also congruent. Why? Because the third side, according to the Pythagoras theorem, what is the value of BC? BC equals to, according to the Pythagoras theorem, the square root of 5 square minus 4 square. 5 squared is 25, minus 4 squared is 16, 25 minus 16 is 9, and the square root of 9 is 3. Here also, so BC equals to 3, and EF also equals to the square root of 5 square minus 4 square, that is 3. So we actually found out that if we have two right triangles that they congruent to each other but their hypotenuse and one perpendicular, then the third side must also congruent. Therefore, we found out that in our triangles we have one perpendicular, and the hypotenuse, the perpendicular and the hypotenuse congruent in those two right triangles. Therefore, the third side must also congruent. Therefore, those two right triangles will be congruent to each other according to side rule. So here we can write down that triangle COD is congruent to triangle OCM according to side rule. Why? Because they have one perpendicular and the hypotenuse that congruent. Here I showed you that the third side must also congruent, therefore those two triangles congruent to each other according to side rule. And from the fact that they congruent to each other, we will derive that DC equals to CM. DC equals to CM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles congruent to each other, therefore the corresponding sides, that is to say DC and CM, must be also equal to each other. But it is given as the question that DC equals to 8 units. You can write down that DC equals to 8, and from this equation 8 equals to DC equals to CM, we will derive that CM is also equals to 8 units. Here CM equals to 8 units. Okay, in the next step I will present to you rule number 11, and we will implement rule number 11 in our drawing. What is rule number 11? According to rule number 11, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 11 in our drawing, because in our drawing we have chord AT that intersects with chord MD. Chord AT intersects with chord MD at point C. Okay, again, chord AT intersects with chord MD at point C. Therefore, according to rule number 11, we will get that MC times CD equals to AC times CT. Again, MC times CD equals to AC times CT. Okay, so I write it down. In our original drawing, chord AT intersects with chord MD at point C. point C is the intersection point of chord 18 with chord MD. I repeat again. In our drawing, we have chord AT that intersects with chord MD, it's point C. Therefore, according to rule number 11, we get that MC times CD, MC times CD equals to AC times CT. I'll repeat again, according to rule number 11, we get that MC times CD equals to AC times CT. What is the value of MC? MC is 8 and CD is also 8. Therefore, MC times CD is 8 times 8, that is 64. That is equal to AC. AC equals to capital R minus 2R times CT. CT equals, what is the value of OT? Point O is the center of the big circle. Point T is the point of the big circle itself. Therefore, OT is the radius of the big circle that is equal to capital R. So what is the value of CT? CT equals to 2R plus capital R. So in conclusion, we found out that according to rule number 11, 64 equals to capital R minus 2R times capital R plus 2R. So 64 equals to capital R plus 2R times capital R minus 2R. And according to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to capital R and B equals to 2R. And this expression equals to A squared minus B squared. A is capital R, therefore A squared is capital R squared minus B squared. B is 2R, so minus B squared is minus 2R squared. So in conclusion, we found out that 64 equals to capital R squared minus 2R squared. That is to say, 64 equals to capital R squared minus 2R squared is minus 4R squared. Again, according to what we found out, that 64 equals to capital R squared minus 4R squared. And what is actually the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I'll repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R squared over 4 minus the area of the small circle, that is pi R squared. Here we took pi over 4 as a common factor out of those two expressions, and inside the brackets we left only with capital R squared minus 4R squared. But we just right now found out that capital R square minus 4R square equals to 64. Therefore, we can substitute capital R square minus 4R square by 64 in this equation. And we get that pi over 4 times 64, it is the area of the green shape. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. Okay, so we finished with the second method. In the next step I will present to you how to find out the area of the green shape according to the third method. We have already found out that CO equals to 2R. We know that AO is the radius of the quarter circle that is equal to capital R. We have already found out in the second method that AC equals to capital R minus 2R. We have already found out that this angle equals to 90 degrees, and this angle it is also equal to 90 degrees. In the next step we will complete the quarter circle to a semicircle. We'll extend the radius AO by a straight line until it touches the semicircle. We define the touching point of the extended radius AO and the semicircle as T. So point O is the center of the semicircle, point T is the point of the semicircle itself, therefore OT is the radius of the semicircle that is equal to capital R. We extended the radius AO by a straight line. When you extend a straight line by a straight line, the result is a straight line. So AT is a straight line. So if AT is a straight line, you can see AT as a chord inside the semicircle. And any chord that passes for the center of a semicircle or circle must be the diameter of the semicircle. So chord AT that passes for point O, that is the center of the semicircle, it is the diameter of the semicircle. Okay, AT is the diameter of the semicircle. In the next step, we join points D and T together by a straight line. We join points D and A together by a straight line. Here we created peripheral angle ADT that rests on AT, that is the diameter of the semicircle, and we have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of a semicircle or circle must be equal to 90 degrees. Here we have peripheral angle A and B that rests on A and B, that is the diameter of the circle. Therefore, peripheral angle A and B equals to 90 degrees. We can implement rule number 5 in our drawing, because in our drawing we have peripheral angle ADT that rests on AT, that is the diameter of the semicircle. Therefore, peripheral angle ADT equals to 90 degrees according to rule number 5. Here, this peripheral angle ADT equals to 90 degrees. Okay. In the next step, we define angle ATD as alpha and angle TAD as beta. And we will focus on the right triangle, triangle ADT. In the right triangle, triangle ADT, this angle equals to 90 degrees. Therefore, the sum of the two other angles, that is to say alpha plus beta, must be equal also to 90 degrees, because of the fact that the sum of the angles in any triangle is equal to 180 degrees. So alpha plus beta must be equal to 90 degrees. We subtract alpha from this equation and we get that beta equals to 90 degrees minus alpha. We subtract beta from this equation and we get that alpha equals to 90 degrees minus beta. We'll focus on the right triangle, triangle ADC. In the right triangle, triangle ADC, this angle equals to 90 degrees. This angle equals to beta. Therefore, this angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. It is the sum of the angles in any triangle. So this angle equals to 90 degrees minus beta, but we have already found out that 90 degrees minus beta equals to alpha. Therefore, we can write here that this angle equals to alpha. Likewise, we focus on the right triangle, triangle CDT. In the right triangle, triangle CDT, this angle equals to alpha. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to beta, so we can write here that this angle equals to beta. In the next step, we will prove that those two right triangles, triangle ADC and triangle CDT, the two right triangles, are similar to each other. So I write it down. We will prove that the right grand triangle, triangle ADC, is similar to the right grand triangle, triangle CDT. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So this angle, it is angle ADC, is equal to this angle, that is actually angle CTD. In addition, those two angles, they are both equal to beta, therefore they are equal to each other. So this angle is angle CAD. That is equal to this angle, that is actually angle CDT. And finally, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So angle ACD is equal to this angle, that is actually angle DCT. So we actually prove that those two right triangles are similar to each other according to angle similarity rule. I write it down. Triangle ADC is similar to triangle CDT according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we'll conclude that the following relationship exists between their sides. We'll conclude that AC over CD equals to CD over CT. I'll repeat again. We conclude that AC over CD equals to CD over CT. AC equals to capital R minus 2R. CD equals to 8. What is the value of CT? CT equals to 2R plus capital R. I'll repeat again. We found out that according to equation number 1, capital R minus 2R equals to 8 over capital R plus 2R. Here we cross multiply this equation, equation number 1, and we get that according to equation number 1, 8 times 8 is 64, and 64 equals to capital R plus 2R times capital R minus 2R. So according to equation number 1, 64 equals to capital R plus 2R times capital R minus 2R. We have already found out that this expression equals to capital R squared minus 4R squared. So in conclusion, we found out that according to equation number 1, 64 equals to capital R squared minus 4R squared. But what is the area of the green shape? The area of the green shape it is equal to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R squared over 4 minus the area of the small circle that is equal to pi R squared. Here we took pi over 4 as a common factor out of those two expressions, so inside the brackets we left only with capital R squared minus 4R squared. But we just right now found out that capital R squared minus 4R squared equals to 64. Here, so we can substitute capital R squared minus 4R squared by 64 in this equation, and we get that it is pi over 4 times 64. 64 over 4 is 16. So this expression in total equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers it is equal to 50.265 square units. We finished with the third method and the second question. In the next step I will summarize the lecture. We'll start with the first question, of course. So here in the problem we have square ABCD inside square ABCD we have a circle. We know that angle CBT equals to 30 degrees, line segment PD equals to 5 units, and our mission is to find out the area of this circle. So first of all we define the center of the circle as O. we have the radius OP that is drawn to the point of tendency, therefore this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. We have the radius OQ that is drawn to the point of tendency, therefore this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. We know that all the angles inside square ABCD are right angles, so those 4 angles are all right angles in square ABCD. So in quadrilateral AQPO, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. In quadrilateral AQPO, we have 4 right angles, therefore quadrilateral AQPO is a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say, AQ equals to PO, but PO equals to R, according to what we already found out. And from this equation, R equals to PO equals to AQ, we derive that AQ is also equals to R. Here, AQ is also equals to R. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we get that AP equals to QO, but we already found out that QO equals to R. And from this equation, AP equals to QO equals to R, we will derive that AP equals also to R. AP equals to R, so we found out that quadrilateral AQPO is not a rectangle but a square because of the fact that all of its sides are equal to each other, they are equal to R. Then we know that all the sides of square ABCD are equal to each other. That is to say, AD, side AD equals to side AB. Or AB equals to AD. What is the value of AB? AB equals to R plus QB. What is the value of AD? AD equals to R plus 5. Therefore, we found out that R plus QB equals to R plus 5. Here we subtracted R from this equation. We found out that QB equals to 5 units. QB here equals to 5 units. Then I presented to you rule number 2 and we implemented rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point, point P. From the common external point, point P, we have tangent PA and tangent PB. And according to this rule number 2, they are equal to each other. That is to say, PA equals to PB. We implemented rule number 2 in our drawing. In our drawing, we have the common external point, point B. From the common external point, point B, we have tangent BQ and tangent BS. And according to rule number 2, they are equal to each other. That is to say, BQ equals to BS according to rule number 2, but we have already found out that BQ equals to 5, so from this equation 5 equals to BQ equals to BS, we will derive that BS is also equals to 5 units. Here BS equals to 5 units. Okay, then we join points Q and S together by a straight line. In this way we get a triangle QSB. What is the size of this angle? The size of this angle it is equal to 90 degrees minus 30 degrees, that is 60 degrees. So this angle equals to 60 degrees and side BQ equals to side BS, they are both equal to 5 units, therefore they are equal to each other. So in front of those equal sides in triangle QBS, there must be equal angles. So those two angles that are located in front of equal sides must be also equal to each other. So if this angle is alpha, this angle must be also equal to alpha. So those two angles must be both equal to alpha. Okay, and this angle equals to 60 degrees. Therefore, the sum of the other two angles must be equal to 180 degrees minus 60 degrees. That is to say, alpha plus alpha must be equal to 180 degrees minus 60 degrees, that is 120 degrees. Here, alpha plus alpha must be equal to 120 degrees, that is to say, alpha plus alpha is 2 alpha, so 2 alpha equals to 120 degrees. So here we divided this equation by 2 and found out that alpha equals to 120 degrees over 2, that is 60 degrees. So here all the angles in triangle QBS are equal to 60 degrees, therefore triangle QBS is an equilateral triangle. And we know that in an equilateral triangle, all the sides are equal to each other. That is to say, QB equals to SB equals to 5 units, therefore the missing side, that is to say, side QS also must be equal to 5 units. Then we join points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of the circle that is equal to R. We have the radius OS that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. Then I copied quadrilateral QBOS in the new page and we analyze quadrilateral QBOS. So this is quadrilateral QBOS that I copied from the original drawing. Those two angles are both equal to 90 degrees. This angle equals to 60 degrees. So what is the size of the missing angle? The missing angle must be equal to 360 degrees. That is the sum of the angles in any quadrilateral minus the sum of the three other angles. So that is to say, the missing angle QOS must be equal to 360 degrees minus 90 degrees plus 90 degrees plus 60 degrees, that is 240 degrees. So the missing angle SOQ must be equal to 360 degrees minus 240 degrees, that is 120 degrees. So I found out that this missing angle equals to 120 degrees. Then I presented to you the law of cosines, and we implemented the law of cosines in this great triangle QOS. What is the law of cosines? The law of cosines is true in any triangle. So if we have this triangle ABC that could be any triangle, side AB equals to A units, side AC equals to B units, and side BC equals to C units, and the angle between side AB and side AC is theta, then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. We implemented the law of cosines in this triangle QOS. Here QS equals to 5, QO equals to R, OS equals to R, and this angle equals to 120 degrees. So according to the law of cosines, we get here that 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. Okay. 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. According to the law of cosines, 5 squared is 25. R squared plus R squared is 2R squared. Minus 2R times R is minus 2R squared, and cosine 120 degrees is minus 1 half. So substitute cosine 120 degrees by minus 1 half. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus. So in conclusion, this expression equals to plus R squared. Therefore, 25 equals to 2R squared plus R squared, that is 3R squared. 25 equals to 3R squared. We divided this equation by 3 and found out that R squared equals to 25 over 3, and the area of any circle is pi R squared. So the area of a circle is pi R squared, but we already found out that R squared equals to 25 over 3. Therefore, we can substitute R squared in this equation by 25 over 3. We did it. We got that the area of our circle equals to pi times R squared, and R squared is 25 over 3. Therefore, in conclusion, found out that the area of our circle equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. We finished with the first question, then I presented to you the second question, and we solved the second question in 3 different methods. In the drawing, we have a quarter circle. Inside the quarter circle, we have a small circle. Line segment CD equals to 8 units. Angle ACD equals to 90 degrees. And our mission is to find out the value of the area of the green shape. So we define the center of the small circle as J. Here, JE is the radius of the small circle that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. And we have JF, that is the radius of the small circle that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle equals to 90 degrees. We define the radius of the small circle as R. Because of the fact that A or B is a quarter circle. It means that point O is the center of the quarter circle. This angle equals to 90 degrees, and AO is the radius of the quarter circle that we define as capital R. Okay, then so AO is the radius of the quarter circle. AO is a radius, it must be a straight line. If we focus on this side of the straight line AO at point C, the sum of the angles here must be equal to 180 degrees. So which angles we have here? This angle equals to 90 degrees, plus this angle, in total they must be equal to 180 degrees. Therefore the missing angle must be also equal to 90 degrees. Okay, so this angle equals to 90 degrees. From point J we go perpendicular on CO. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point J in CO as T. So inside quadrilateral CEJT, the upper quadrilateral, we have 1, 2, 3 at angles, therefore the fourth angle must be also equal to 90 degrees. Inside the lower quadrilateral TJOF, we have 1, 2, 3 at angles, therefore the fourth angle must be also equal to 90 degrees. Therefore, angle EJF, this angle equals to 90 degrees plus 90 degrees, that is 180 degrees. Angle EJF equals to 180 degrees, therefore angle EJF is a straight line. If angle EJF is a straight line, then EJF is also a straight line, and if EJF is a straight line, then line segment EF is also a straight line. And if line segment EF is a straight line, it means that quadrilateral CEFO is a rectangle. Why? Because quadrilateral CEFO has 4 right angles. And you know that the opposite sides of a rectangle are equal to each other. That is to say CO equals to EF. But we have already found out that EF equals to R plus R, that is 2R. So from this equation CO equals to EF equals to 2R, we will derive that CO is also equals to 2R. Then we join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself. Therefore, OD is the radius of the quarter circle that is equal to capital R according to our definition. Then we implemented the Pythagoras theorem on the right green triangle, triangle COD. According to the Pythagoras theorem, OD square equals to CD square plus CO square. Repeat again. According to the Pythagoras theorem, OD square equals to CO square plus CD square. OD is capital R, therefore OD square is capital R square. CO is 2R, therefore CO square is 4R square. CO square is 2R square, that is 4R square. CD is 8, so CD square is 8 square, that is 64. So in conclusion, we found out that according to equation number 1, capital R square equals to 4R square plus 64. We subtracted 4R square from this equation and found out that according to equation number 1, capital R square minus 4R square equals to 64. What is the area of the green shape? From the domain it is very easy to see that the area of the green shape equals to the area of the quarter circle minus the area of the small circle. Repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle equals to the area of the circle, that is pi times capital R square over 4, and the area of the small circle is pi R square. Here we took pi over 4 as the common factor, so what is left from pi times capital R square over 4 after we took from it pi over 4 as the common factor? What is left is actually capital R square. What is left from minus pi R square after we took from it pi over 4 as the common factor? What is left is actually minus 4R square. Why? Because minus 4R square times pi over 4 equals to exactly to minus pi R square. But we have already found out that capital R square minus 4R square equals to 64. Therefore, we can substitute capital R square minus 4R square here by 64. We did it, and we got that this expression in total equals to pi over 4 times 64. 64 over 4 is 16. So in total, this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the first method. Then I presented to you how to find out the area of this green shape according to the second method. in the second method use for the things that we have already found out in the first method. That is to say, we have already found out that CO equals to 2R, AO is the radius of the quarter circle that is equal to capital R. This angle equals to 90 degrees and this angle equals to 90 degrees according to what we have already found out in the first method. What is the value of AC? AC equals to AO minus CO. Again, AC equals to AO minus CO. That is to say, AC equals to AO, that is capital R, minus CO, that is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. Then we completed the quarter circle to a circle. We extended the radius AO by straight line until it touches the circle at point T. Point O is the center of the big circle. Point T is the point of the big circle itself. Therefore, OT is the radius of the big circle that is equal to capital R. Then we extended the straight line DC by straight line until it touches the circle at point M. When you extend the straight line by straight line, the result is a straight line. Therefore, MD must be a straight line. If you focus on the lower side of the straight line MD at point C, here the sum of the angles must be equal to 180 degrees. Which angles we have? At the lower side of MD at point C, we have this angle that is equal to 90 degrees. Plus the missing angle, in total, they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 90 degrees in order to complete the sum of the angles in the lower side of MD at point C to 180 degrees. This angle must be equal to 90 degrees. So we have here two right triangles, triangle COD and triangle COM. We proved that those two right triangles can go into each other. Why they can go into each other? First of all, we have side CO that is a common side that belongs to both triangles, so CO equals to CO is a common side. We have side OD is equal to side OM, they are both the radii of the big circle, therefore they are equal to each other. I repeat again, here we have side CO that is equal to itself, so OM equals to OD, they are both the radii of the big circle, therefore they are equal to each other. By proving that the hypotenuse and one perpendicular in those two right triangles can go into, we prove that those two right triangles can go into each other. Why? Because if, for example, we have two right triangles that are equal between them in their hypotenuses and with one perpendicular, here DF equals to AC equals to 5 units and DE equals to AB equals to 4 units, then the third side, that is EF in this triangle and BC in this triangle, must also can go into. Why? Because according to the Pythagoras theorem, the value of the third side, here it will be equal to the square root of 5 units minus square root of 4 units, that is 3. So we found out that if we have two right triangles that has the same hypotenuse and the same perpendicular, then the third side must also can go into. Therefore, those two right triangles we can go into each other according to side rule. Okay? And for the fact that they can go into each other, we will derive that DC equals to CM according to the rule that corresponding sides that can go in triangles are equal to each other. But we have already found out that DC equals to 8, so from this equation 8 equals to DC equals to CM, we will derive that CM is also equals to 8. Here CM is also equals to 8. Then I presented to you rule number 11 and we implemented rule number 11 in our drawing. According to rule number 11, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. You can implement rule number 11 in our drawing, because in our drawing we have chord AD that intersects with chord MD at point C. Again, chord AT intersects with chord MD at point C. There, I repeat again, here, chord AT intersects with chord MD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. Again, MC times CD equals to AC times CT. I repeat again, according to rule number 11, we get that MC times CD equals to AC times CT. MC equals to 8, CD equals to 8, so MC times CD is 8 times 8, that is 64. AC equals to capital R minus 2R, CT equals to capital R plus 2R. Therefore, we found out that according to the equation, according to rule number 11, 64 equals to capital R plus 2R times capital R minus 2R. this expression capital R plus 2R times capital R minus 2R, according to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to capital R and B equals to 2R. So this expression must be equal to A squared minus B squared. A is capital R, so A squared is capital R squared minus B squared. B is 2R, so minus B squared is minus 2R squared. So in conclusion, we found out that 64 equals to capital R squared minus 2R squared. That is to say, 64 equals to capital R squared and minus 2R squared and minus 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. What is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle is pi times capital R squared over 4. The area of the small circle is pi R squared. We took pi over 4 as a common factor of those two expressions. Inside the brackets, we left only with capital R squared minus 4R squared. What we just right now found out that capital R squared minus 4R squared equals to 64. Therefore, we can substitute capital R squared minus 4R squared in this equation by 64. We did it and we got that the area of the green shape equals to pi over 4 over 64. 64 over 4 is 16. So in total, this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the second method, then I presented to you how to find out the area of this green shape according to the third method. In the third method, here we have already found out that AC equals to 2R in the first method. AO equals to capital R. We have already found out in the second method that AC equals to capital R minus 2R. This angle equals to 90 degrees and this angle equals to 90 degrees according to what we have already found out in the previous methods. Then we completed the quarter circle to a semicircle. We extended the radius AO by a straight line until it touches the circle at the semicircle at point T. Point O is the center of the semicircle. Point T is the point of the semicircle itself, therefore OT is the radius of the semicircle that is equal to capital R. When you extend the straight line by a straight line, the result is a straight line. Therefore AT is a straight line that passes. If AT is a straight line, we can relate to AT as a chord. So we have chord AT that passes through the center of the semicircle. Therefore, chord AT must be the diameter of the semicircle. Why? Because any chord that passes through the center of the semicircle must be the diameter of the semicircle. Therefore, AT is the diameter of the semicircle. We joined points A and D. We joined points D and T. In this way, we created peripheral angle ADT. Peripheral angle ADT rests on AT, that is the diameter of the semicircle. We have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of a circle or a semicircle must be equal to 90 degrees. So we have here peripheral angle A and B that rests on the diameter of the circle that is AB. Therefore, peripheral angle A and B equals to 90 degrees according to this rule number 5. We can implement rule number 5 in our drawing, because in our drawing we have peripheral angle ADT that rests on AT, that is the diameter of the semicircle. Therefore, peripheral angle ADT equals to 90 degrees according to rule number 5. Then we define the angle ATD as alpha. Angle DAT is beta. So in the right triangle ADT, this angle equals to 90 degrees. Therefore, the sum of the other two angles must be also equal to 90 degrees according to the rule that the sum of the angles in a triangle is 180 degrees. So here alpha plus beta must be equal to 90 degrees. We subtracted alpha from this equation and found out that beta equals to 90 degrees. minus alpha. Then we subtracted beta from this equation and found out that alpha equals to 90 degrees minus beta. Then we focused on the right triangle, triangle ACD. The right triangle, triangle ACD, this angle equals to beta. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees, it is the sum of the angles in any triangle. So this angle must be equal to 90 degrees minus beta. But we have already found out that 90 degrees minus beta, 90 degrees minus beta equals to alpha. So we can substitute 90 degrees minus beta here by alpha. Likewise, in the right triangle CDT, this angle equals to alpha, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to beta. So we can substitute 90 degrees minus alpha here by beta. Then we proved that the right green triangle, triangle ADC, is similar to the right green triangle, triangle CDT. So those two right triangles are similar to each other. Why they are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So we proved that those two right triangles are similar to each other according to angle similarity rule. And for the fact that they are similar to each other, we will derive that AC over CD equals to CD over CT. I repeat again, AC over CD equals to CD over CT. AC equals to capital R minus 2R, CD equals to 8, and CT equals to capital R plus 2R. We cross multiplied this equation and found out that 64 equals to capital R plus 2R times capital R minus 2R. But we have already found out that this expression capital R plus 2R times capital R minus 2R equals to capital R square minus 4R square. So in conclusion, we found out that according to equation number 1, 64 equals to capital R square minus 4R square. But what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle, that is pi R square. We took pi over 4 as a current factor, so inside the brackets we left only with capital R square minus 4R square. But we just right now found out that capital R square minus 4R square equals to 64. Therefore we can substitute capital R square minus 4R square by 64. We did it and we got that this the green shape, the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16. So in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. So in all three methods we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. Okay, thank you very much.